also from electrical engineering and also from National Taiwan University, and is today working in the same lab, the DSP IC lab, as the speaker before. But he majors also in hardware, so he does also VLSI architecture design, not only 3D video algorithms. And we're looking forward to his presentation on compressive sensing-based client cloud systems for 3D depth reconstruction. So welcome, and the floor is yours.
Okay. Ladies and gentlemen, my name is Chung-Yu from DSP IC Design Lab, National Taiwan University. Today, my presentation topic is compressive sensing-based client cloud system for 3D depth reconstruction. Here is my outline of today's presentation. First, I'll show the motivation and briefly introduce this work. Second, I'll introduce my system framework by 3 parts as shown on the slide. Third, demonstrations and experimental results will be shown to prove our feasibility. Next, I'll conclude this work. Nowadays, various information dominates the world, and information transmission is an indispensable part of modern technology and in our daily life. For example, robots needs to acquire the depth map of the surrounding like this short film. Yes, and with only these remote devices, it may not possess enough powerful computation capability. So we just add a computing center on it, and we set up a client cloud system to handle this whole data stream. Yes, yet another, wireless resources are very expensive and limited. So we try to focus on how to lower down the transmission bandwidth. Introduction. Our work is divided to 3 parts: client cloud system, compressive sensing, and feedback and correction mechanism. Cloud computing is a future trend. I think many of you have tried this and even familiar with it. Cloud computing has many benefits. It can divide the whole system into client part and cloud part, and each part specializes in its job. And next, we apply compressive sensing theory to this. Compressive sensing is a novel signal processing technique. It can reduce measurement to compress. And its properties, simple encoding and complex decoding, it can just fit the client cloud system, the cloud computing technique. And last, we perform feedback and correction mechanism to automatically check the result, whether the result is right. This is our proposed system framework. We can follow the top-left depth image and the errors to understand the system framework, system flow. And we can now, sorry. Yes. And first, we preprocess our depth image with subtraction and denoise with truncation. Then we multiply a random matrix to compress this signal and deliver it to cloud part. Cloud part computing to reconstruct the original signal and verify if it is right. If it is wrong, then it sends the feedback signal to client part to require more measurement. And if it is right, then we add to the last frame to get the correct frame. Then the whole work can roughly divide to 3 parts: sparse representation, dynamic compressive measurement, reconstruction and correction mechanism. I will successively introduce the details. Sparse representation. To apply compressive sensing, we must find the signal's sparse representation. As we know, the adjacent frames, like these two images, is very similar. We cannot tell the difference between it. But when we subtract the current frame, the next frame from the current frame, we can get the slightly difference, which often indicates to the edge of moving objects. Then this is a sparse signal. To enhance the sparsity of this signal, we truncating small values. As we know, there are many noise in every sequences, so we truncate to make the compressive sensing recovery theory more robust. Second idea is dynamic measurement. The dynamic measurement is an application of compressive sensing. The compressive sensing is a novel signal processing technique. It lets us to compress signal very easy. When we can see x, if x is an n by 1 vector, then we just multiply a random matrix by n by n, where n is less than n. Then we can get another signal y, which is n by 1. Then the compression is done. And the compressive sensing notes that x can be reconstructed from y under the condition n larger than or equal to ck log n over k, where c is a constant. Then the k here is a very important factor. K is, if the x is k sparse, this is definition. We say x is k sparse if the number of non-zero entry of x is k. Then we say it is k sparse. Under this condition, y can be reconstructed. Then we know frames sparsity varies with frames, so we can calculate the least needed measurements n. And this measurement, we can calculate the least needed and multiply to x, then we can compression it. The third idea is reconstruction and correction mechanism. Cloud power will recover the original signal by solving L1 minimization problem, whose definition is on the slide. And we can, so after solving L1 minimization problem, we get an estimated difference. In this case, it's D prime. We can check if the D prime is reconstructed right. Yes, and we compute error E by multiplying D prime with the same random matrix phi and subtract y and get L2 norm to get this error E. Oh, okay. Thanks. Then if the error is smaller than or equal to the threshold is fixed, then we can consider the result is right. Then add to the next frame, and we get the new reconstructed frame. And on the other hand, if error larger than threshold, then we consider result wrong. If the result wrong, the cloud part and transmit the feedback signal to the cloud part to request more measurement. The client part then transmit supplementary measurement YS and supplementary random matrix YS to the cloud part. The cloud part then append to the original YT and phi-T. Then we get new phi total and Y total. Use this new pair of Y total and phi total, we can solve the more correct result. The upper is our reconstructed result, and the lower is the original frame. You can see that it is almost the same because this is fully reconstructed. It is good. And the other sequence, is not so good, and it has some error frames and image retention. You can see it on the upper. You can see image retention. Yes, this is mainly because the view window are changed, so the difference of two frames are larger. Yes, this is our experimental result. And you can see that our dynamic method compared with fixed method. The definition of average error and error frames are on this slide. The fixed method n equals to 1000. And we can see that sequence 1 even half of the sequence are wrong. Though use more measurement, but the dynamic method eliminates all error. Then we raise the measurement to 2000. We can see error frames are low down, but it still has error, not like dynamic. And we further raise up to 3000, and there's still some errors. So our dynamic method is perform well. Okay, this is the numerical data. We can see that n equals to 2000, where measurement reduce about at least 19%. And if n equals to 3000, our dynamic measurement reduce about at least 46%. This is what distribution of the sparsity K and the corresponding compressive measurement N of 3D sequences. We can see the sparsity varies, waves, and measurement. Our dynamic measurement also waves. Yes. If we set up a fixed measurement here, then we must have some error. And on the other sequence, this is the same fluctuation too. In conclusion, we proposed a compressive sensing-based client cloud system for 3D depth reconstruction. The overall transmission bandwidth is significantly reduced with dynamic compressive sensing. Generally, the proposed framework can be further applied to other signals with a similar computer manner. In our future work, latency is a big problem, while solving L1 minimization problem is not so easy, even worse when feedback is involved. And high resolution is the future trend. And our reconstruct frame are based on the less frame, so the error propagation, we should much more reduce it. And we can apply to our signal if we include machine learning theory. That it to find a sparse representation automatically. Okay, thank you. This is our report.
Thank you very much, and thank you especially for being that brave. So typically people become very nervous if the computer breaks down, but you behaved very cool, like it was no problem. So we lost only 30 seconds overall. So
thank you very much.
Excellent. Are there any questions from the auditorium? Yeah.
I was wondering, could you do this reconstruction test already on the server side, so you don't need the feedback for sending a bigger file matrix? So maybe you could try it on the server first?
Oh, yes, yes.
Yeah.
Yes, yes. Okay.
Dangerous.
The render matrix file, it is already saved in the cloud part and the client part. It is the same.
Oh, okay.
Yeah.
Further questions? We still have time for one question. Yeah.
What are you doing with the reconstructed image in the cloud? Because the cloud is somewhere and you have to get it back somehow. How do you get it back, your reconstructed image?
You mean feedback?
No. You have to get your reconstructed depth image back.
All reconstructed images on the server side. It is the purpose. Could you mention your question again?
You send your image to the cloud, right?
Yes.
Do some kind of whatever processing to it.
Yes.
And then you have to get it back. Why not?
No.
It's just a sensor.
Just send to the cloud part and it's over. The client part is just remote devices. We don't need to send back to him.
Okay.
Okay, thank you.
I would have one question. The difference, what you call subtraction, at the moment you make from frame to frame, right? So in the temporal domain. If your sensor is moving, because it's like an environmental sensor, would you also apply like a kind of motion compensation for the difference, or the pan compensation for the difference?
Yes.
Because that would make the difference image smaller.
Yes. If the view window is moving, our system is perform worse.
Yeah.
Yes, it may be a future work.
Yeah, I mean, you could simply add, if you know what your sensor is doing, you could simply add the motion and make the subtraction motion dependent.
Oh, of course. Thank you, your suggestion. Thank you.
Okay, thank you very much for